Hey, good morning, everyone. So I'm Longfei from Princeton. So today I'm going to talk about our recent work on the mobile RFID tag sorting robot. It is called the MobiTagbot. So this is a joint work with my advisor at Princeton, Cal Jameson. So in my childhood, I'm crazy for the Harry Potter. But at that time, I don't have enough money to buy a library card. So each time after I reading the book, I will hide that book in a corner of the bookshelf to make sure no one else can find it and borrow it. So actually, hiding books was a lot of fun to me. But as I grew up, I finally realized that, it brings a lot of troubles to the librarians. Every year, the librarians need to sort the library books to find those misplaced books. To do so, actually they need to visually checking each book on each layer of each bookshelf. This process is time-consuming and error-prone. For example, to sort in a library with over 1 million books here, it needs at least 10 librarians to sorting for a whole week. And also, during the sorting process, people may get fatigued, so they will make mistakes. Well, during the past decades, millions of RFID tags are deployed in the retail stores, the warehouse, and also the libraries. So, once these tags are attached to different items here, the location of these tags essentially reflects the location of these items in the warehouse, library, or the supermarket. Noticing that, an intuitive idea here to replace the labor-intensive book sorting process is to use this machine-based tag localization system. Well, during the past, you can see there are a lot of effort for the RFID-based localization system. However, this system are not suitable for the book sorting. For example, Pinnet, which presented in SICOM, it requires abundant anchor tags, and also its localization accuracy is just around 10 centimeters, which may cover 5 or 6 books here, so it cannot be used for sorting books. Well, another representative work here, the tagogram, the tagogram here requires the known location and the orientation of the reader antenna. And also, its performance is susceptible to the multipath. Let's see how these schemes works. Actually, they are inspired by the auto reader system. So here, I use a two-dimensional localization scheme to explain the reader principle. Suppose the reader is composed of 3 antennas here, and we want to use this reader to localize the plane in the air. So we first split the space into the same size blocks here, and we assume the plane is on one of these block here. So here each antenna will send a wire signal to the sky, and then record the phase reading of each signal that bounces off the plane. On the other hand, the reader here could compute the theoretical phase reading, which the signal bounces off each block in the sky. So, after receiving those real signals that's reflected by the plane, the radar system can correlate the received phase reading with the theoretical phase reading at each block. So the location here with the highest likelihood should be the estimated location of the plane. So this is a basic principle of those phase correlation-based scheme. Well, similar to the auto-rated system, in the book sorting scenario, we can find that we can first divide the bookshelf into small blocks and then compute the theoretical phase readings here that bounces off each block here. So when receiving the signal from the tag, we can correlate the phase reading with the theoretical phase reading at each location using this correlation idea. So similar to the radar system, the location with the highest likelihood should be the estimated location of the tag. However, when adopting this idea for the tag localization, more antennas will lead to a higher accuracy. So this is basically because the face reading has ambiguity problems here, and more spatially separated antennas will help to eliminate the face ambiguity problem. So just as this figure shows, when there is only 2 antennas, we can see a grating lobe appears. Well, as we use 3 antennas, we can see the grating lobe gets weakened. And the grating lobe is almost disappear as we use 4 antennas. However, the infrastructure here quickly becomes burdensome with more antennas. So here comes the question: can we build up an autonomous tag sorting robot use possibly, the minimum number of antennas here? So the answer is yes. Here, we present the design and implementation of this MobiTagbot. Actually, MobiTagbot works by sweeping tagged books in each layer of the bookshelf. Based on the collected face readings of each tag, it then estimates the location of each book and then sorting them. Well, in MobiTagbot, the antenna is put on top of the Roomba. As this figure shows, when the reader moves, it queries the RFID tag at different locations. Hence, we virtually build up an antenna array during the antenna's movement. So with the face reading received at different locations, we could get more accurate result here. Well, suppose the antenna collects the data at n locations here. Then we basically create n virtual antennas for tag localization. However, as we will see later, these face readings may not be enough to get a higher accuracy due to the face ambiguity problem. So in MobiTagbot, we also round-robin different channels at each location. So by doing so, we virtually create more antennas here, and they can help to improve localization accuracy. So as this figure shows, when we create the hologram without the channel hopping, we can see that 2 grating lobes exist. And this grating lobes makes the true location of the tag hard to be distinguished. Well, if we run robin 16 channels at the same number of locations, we can see the grating lobes here decrease significantly, and the likelihood of the true location of the tag increases. Hence, we can easily distinguish the true location of the tag here. So here we implement a prototype of this face correlation-based scheme using the commercial off-the-shelf RFID reader, a hacked version Roomba, and also 2 antennas. So the system here is fully implemented in Java, and we use the low-level reader protocol to interrogate the tags here. So let's look at the performance of the simple face correlation alone. So this figure shows the CDF of the error distance achieved by this correlation-based scheme. As we can see here, the median accuracy is about 4.3 centimeters, and the 90th percentile is just around 6.4 centimeters. Well, this localization error seems promising. Unfortunately, the thickness of most books is very small, maybe just around 2 or 3 centimeters here. So as this figure shows, 4.3 centimeter error margin may cross 3 books here. So if we use the face correlation-based scheme here, we may get the wrong order of these books. So where does the error margin come from? Yeah, it is from the multipath propagation. We know in indoor place, the wire signal will bounce off different objects and then arrive at the tag. So the similar things happen from the tag to the antenna. So, since the theoretical phase reading here are computed only along the length of that path here, so the system may run into the problem when working in prevalent multipath environment, just like the library and the warehouse. People may, where people may just walk around to create multipaths. To acquire, to acquire more accurate localization results, we need to eliminate or minimize the impact of this multipath effect. So how to detect the multipath effect here? So our key intuition here is that, in low multipath environment, since the signal propagates along the length of that path, so if we linearly change the working frequency of the sending signal, we are expected to see the linear changing trend of the received phase readings, just as this figure shows. And in contrast, in the prevalent multipath environment, since the received signal is a combination of the signal propagates along multiple paths, so the aggregated phase reading does not change linearly as we linearly decrease the working frequency of the reader. So based on this observation, our MobiTagbot system works as follows. At each location, it first round-robin different channels and tests the linearity of the received phase trend. If the multipath is strong, it will omit the measurement at the current location. Otherwise, it will include these phase readings for the hologram generation to get the location of each tag. So here, to test the effectiveness of our multipath suppression algorithm, we conduct a macro benchmark. So in this experiment, we attach 20 tags on a board, and then we let the robot to sweeping all these tags. So as we talked before, the median error of the phase correlation-based scheme is not very accurate. It's just about 4.3 centimeters, which we know is not precise enough for book sorting. Well, as we process the phase readings using the multipath suppression algorithm, we can see that the MobiTagbot it achieves about 2.9 centimeters median error distance, which is about 1.5 times more accurate than the phase correlation-based scheme. Here we briefly talk about the MobiTagbot's performance. So actually we conduct the first field study to evaluate MobiTagbot in both the prevalent and the low multipath environments. So in each scenario here, we attach 20 tags on 20 books, and then we use our system to sort these books. And besides, we also compare our scheme with two state-of-the-art, Tagoram and STPP. So let's first look at how these three schemes perform in prevalent multipath environments. So this figure shows the CDF of the error margin achieved by the STPP in prevalent multipath environment. As we can see from this figure, it achieves about 8.4 centimeters median accuracy, which we know is still not enough to sorting the books in the library. Well, Tagoram achieved a better performance with an accuracy around 5.6 centimeters. However, this error margin is still too large to sorting books, as the thickness of the normal book is still just around 3 or 2 centimeters here. Well, we can see the MobiTagbot achieves a median error margin about 3.4 centimeters, outperforming both the Tagoram and STPP. So the main reason behind is that the MobiTagbot can drop the phase readings collected from the prevalent multipath environment locations. Well, this figure shows the CDF of the STPP in the low multipath environment. we can see here that the SPP can achieve a median accuracy about 7.4 centimeters, which is better than its performance in the high multipath, the prevalent multipath environment. However, the error margin is still significantly larger than the thickness of the normal books. Well, for the tagogram, it achieves a median accuracy around 3.8 centimeters, much better than the STPP. Well, let's look at the MobiTagbot. We can see that it achieves a median accuracy about 2.8 centimeters, which outperforms the tagogram and STPP by a factor of 1.3 and 2.6. So apart from the field studies in both the low and the prevalent multipath environment, we also conduct the micro benchmark to test the parameter settings in our system, just like the number of channels we use, the channel bandwidth, and also the number of tags. Well, due to the time limitation, I will not go into the details about the result here. Well, here comes the conclusion. So the MobiTagbot is actually the first tag ordering robot which can achieve a centimeter scale accuracy. And in the MobiTagbot, we design an algorithm to detect and rejecting the phase readings where the multipath reflections are very strong. And also, we systematically evaluate the MobiTagbot with and compare its performance with two state-of-the-art, which can demonstrate that the effectiveness and accuracy of our system. So that's all for my presentation. Thank you.